Quantified statements. First, we've got to know what the root word of quantify is. So the root word in quantified or quantify is quantity. And how do we measure quantity? We measure a quantity as whole or sum or none at all. So all of something, a bit of something, part of something, which is sum, or nothing at all, in which case none. All of those represent quantity, and those are referred to as quantifiers. Because they quantify something in a statement. Here is an example. All cats are lazy. Now, all is the quantifier. Some dogs are aggressive. The quantifier is some. No pigs can fly. No would be the quantifier. In all of those cases, we are simply making statements. So all three examples that I listed are quantified statements because they are statements that contain quantifiers. There are equivalent ways in which we can write a quantified statement. Again, we are trying to get at this from a very logical, formal perspective. In practice, in real life, I'm not going to sit around and carefully come up with a logical statement. We just speak. We learn a language, we reason, we speak. But to formalize logic, to formalize reasoning, things have to be represented in a certain way. So we have this equivalent representation of quantifying statements. The very first one, I'll use the example that I had. All cats are lazy. So the quantifier here is all. Now I want to change and come up with an equivalent statement. The equivalent statement here would be there are no cats that are not lazy. So note some sort of negation going on there, and suddenly all becomes none or no. So something that was full now became empty. So you can see a double negation going on, no, not, which reverts back to all cats are lazy. So those two statements are one and the same. The first one is a simple way of saying all cats are lazy. The equivalent statement is there are no cats that are not lazy. One can formalize this and write it as all P are Q. The equivalent statement would be there are no P that are not Q. Now replace P and Q with anything you want, and it'll just work. The next example that I used is some dogs are aggressive. The quantifier is some. If I say that some dogs are aggressive, there has to be at least one dog that is aggressive. The equivalent statement, there has to be at least one dog that is aggressive. Formalizing this, one can write this as some P are Q. The equivalent statement here, there exists at least one P that is a Q. You can replace P, Q by any statement you want. You should notice that I used has to be with exists. Exists is a very formal term in math and logic, but in practice, you know, same as saying has to be at least one dog that is aggressive. Some dogs are not aggressive. An equivalent statement here for some dogs are aggressive. Oh, excuse me, are not aggressive. I can start with all dogs are aggressive. And if I put a not in front of it, not all dogs are aggressive would mean some dogs are not aggressive. If I rewrite it as all dogs are aggressive and put a not in front of it, to a person who knows the language, it seems the same. So I can simply write, in general, some P are not Q. The equivalent statement will be not all P are Q. You can replace P, Q by anything you want. So you can't take a quantified statement and come up with a statement that is not quantified and call it equivalent. It's not going to work that way. If you look at the first example, all cats are lazy you had a quantifier, so you have to have a quantifier in the equivalent statement. That was no. In the second example, some dogs are aggressive. Well, some is the quantifier. You go to at least one, that is a count, at least one becomes the quantifier. In this case, C, some dogs are not aggressive, some is the quantifier. Not all dogs are aggressive, all is the quantifier. I'm going to go with no mathematicians are statisticians. When we say no mathematicians are statisticians, we are simply saying all statisticians, excuse me, have it backwards. All mathematicians are not statisticians. No P or Q is equivalent to saying all P are not Q. You can put in any P, Q, Q. To generalize, if we combine a quantified statement with negation, negating a quantified statement. I did this earlier in part C. If we say all P are Q, and if I negate, I would end up saying not all P are Q. We know the equivalent statement for that. Some P are not Q. Yes, part C, down here, some P are not Q, equivalent to not all P are Q, but where does not all P are Q come from? It comes from negating all P are Q. So take the example, all dogs are aggressive. If you negate, you would say not all dogs are aggressive, which would simply mean some dogs are not aggressive. So the part right here is equivalence, the part right there is negation. So we can simply suggest that statement, some dogs are not aggressive, comes from negating all dogs are aggressive. I'm going to say some P are Q, negating, you're putting not some P are Q. So if you say some, the opposite of some is none, because some means there is something. The opposite of that would be nothing. So the statement that I can write here is no P R Q. So we can directly suggest that some P R Q, if I negate, I will end up getting no P R Q.